Okay, hello boys and girls. So today I will be discussing a frequentist approach to probability, and this might seem very short, but it's actually the most practical way to estimate the probability of events. And this is the fundamentals of something called Monte Carlo simulations. And before getting into all that, I'll explain what this is. Okay, so consider an experiment that is performed repeatedly. So let's say it's performed n times, and what we are observing is the occurrence of an event A. And I'll take a simple example. Let's say we are throwing a dice. It has 6 sides, 6 numbers, and we are observing the occurrence of 1, the number 1. And yeah, you might say, okay, so the number 1 by 6 is the probability. But no, that is the probability according to the classical approach. So the classical approach, it assumes that 1, 2, 3, 4, 5, 6, they are all equally likely. And so because they are equally likely, the probability of each of those numbers is 1 by 6 according to the classical definition of probability. But the frequentist approach, it does not assume that all the probabilities are equally likely. It does not assume all outcomes are equally likely. What it assumes is, okay, so if I have an experiment that is throwing the dice, and what I'm observing, what I'm looking for is the occurrence of 1. Now suppose the dice is loaded. So what if the dice is loaded so that 1 does not occur frequently, or 1 occurs more frequently? So in that case, what you do is throw the dice n times, look for the occurrence of 1, that is the event A, and record how many times it appeared in those n trials. And once you've completed those n trials, and mind you, n is supposed to be a very large number, like 1,000, 10,000, 100,000, something even more, how much ever time and power you have. So after those number of trials, what you do is assign the probability, or at least you can approximate that the probability of A, that is the occurrence of 1, is the number of times 1 appeared over the total number of trials. So yeah, this is kind of like this is an upgrade to the classical definition of probability, in the sense that it actually accounts for events which are not exactly equally likely, and so we have this estimated probability. But what will happen if the number of trials, that is n, it tends to infinity? In that case, if this limit even exists, then you will have this ratio converge to a constant number that will be the actual probability of A. But the limitation of this is that suppose this Na by n, this ratio as n tends to infinity, it does not converge. And now you may ask, okay, like how will this even happen? And I'll say, so what if each trial is not exactly independent? Now mind you, we assume that in this experiment, each trial that we perform, all this n trials that we perform, were independent of each other. What if that's not the case? What if going forward, the previous trials actually affect the outcome of the trial in the future? What if something like that happens? So in that case, because of some problems in the process itself, maybe this limit won't converge, maybe it will diverge. So if this limit does not exist, there is no meaning to assigning this probability. And so this over here will basically be an estimate for a particular window, that is the n times this experiment has been performed. This will be an estimate, average. And this thing, if it exists, then yeah, this average, as you go forward in the experiment, it will actually converge to a particular number, and that's what we will call the probability of this event A. So this is the frequentist approach. And in the Monte Carlo simulations, what we do is, suppose that we want to find out, suppose we have an example, I'll demonstrate. Suppose all the points that I randomly choose fall within this region. This is a square of side 1. Okay, this is the center of the square. Now what I'm saying is the sample space is basically this square region. Okay, let's just mark this. This square region is your sample space, and whatever point I choose, it will 100% fall into the square region only. Now the question is, if I want my point to fall in this circle that I have drawn, okay, I mean it does not look like a circle, but bear with me here. If I want my points that I choose to fall within the circle, what is the probability of that? Now by classical definition, you will say the probability of, I'll just mark A as the event where point falls inside circle. P of A, you will say that, okay, that is pi times 1 square over 1 square, right? Oh, sorry, pi times 0.5 square. The radius of the circle is 0.5. Yeah, pi times 0.5 square. So that will be pi by 4. This is by the classical definition that I'm saying. Now, in a Monte Carlo simulation, what I'll do is I'll choose random points inside the square. How I'll do that? There are many strategies. You can use a computer. Python provides you the libraries to implement random selection of points. And now the point is that if I choose 10,000 points within the square, how many of them will fall within this circle? And now, if you choose 10,000 points, you will see that the ratio of the points that fall inside the circle to the total number of points I've chosen that fall within the square should approach something close to pi by 4. And yeah, this stuff is actually based on the frequentist approach to probability. And with that, I end my lecture on that. The next video will focus on axiomatic probability, which is much more mathematical in nature compared to the frequentist and classical approach, which seem much more experimental or logical in a way. So yeah, with that, I'll see you in the next video.